So we've recently finished our discussion of Chapter 1, which is about logical thinking. And now we're moving on to Chapter 2, which is about relational thinking. In relational thinking, we explore the relationships among various groups of objects. In this chapter, there will be several topics of relational thinking that will be discussed, including graphs, sets, functions, relations and equivalences, partial orderings, and graph theory. We begin the chapter with a discussion of graphs. We should keep in mind that this discussion of graphs that we're about to embark upon is going to be informal. Later, if we get to the material in section 2.6, we'll then study graphs from a more rigorous point of view. A graph is a diagram. It consists of vertices, which are dots, connected by lines or curves that are called edges. So these edges, they can have a direction, in which case the graph is called a directed graph, as here on the left, or the edges might not have a direction, as on the right, in which case we say that the graph is undirected. So the way to think about a graph is that the dots or vertices represent objects of interest to us, and the edges represent relationships among these objects. For instance, on the graph on the right, V, W, X, Y, and Z could be cities, and maybe the edges represent an edge will join two cities together if there's a single interstate highway joining them. For instance, V and Z joined by an edge indicates that there's some single interstate highway joining V and Z. Now, the edge joining X to itself up here, maybe you would think about that as maybe X is a city that has a loop, like Indianapolis. Another way to think about this, like if you look at the graph on the left, the directed graph, maybe you think of A, B, C, D, and E as being websites, and the edges indicate that one website appears as a link in another website. For instance, maybe this edge from B to C indicates that a link to website C exists within website B. That is, you can get to website C from clicking a link on website B. Like so many things in mathematics, the study of graph theory begins with the famous prolific mathematician Leonhard Euler, who lived in the 18th century. So Euler was told of this Königsberg bridge problem. So Königsberg is a city currently called Kaliningrad in Russia on the Pragal River. In fact, it's an island city and it has 7 bridges. So the Königsberg bridge problem is to see if one can walk around the town and cross each bridge exactly once. So this is the problem that was told to Euler. The Königsberg bridge problem can be translated to a problem about a graph. So if you think about the regions of the city as being regions A, B, C, and D, you can produce a graph whose vertices are A, B, C, and D. And then the existence of a bridge from one region of the city to another induces an edge on the graph. So notice that in the model of the city, there are 2 bridges here joining region A to region B. And so there are going to be 2 edges joining vertex A to vertex B. So the Königsberg bridge problem on this graph is that we would want to travel around this graph using each edge exactly once. So we return to the Königsberg bridge problem in a little bit, but first we need some terminology. A loop is an edge from a vertex to itself. So here in both of these figures we see loops. There's one joining C to itself. There's one joining X to itself. Now the degree of a vertex is a measure of how many times it's touched by edges. So for instance, the degree of X, to find what that is, I want to count the number of edge touches. So I see one here, I see one here, 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 and here. So there are 5 edge touches on X, and so the degree of X is 5. On the other hand, the degree of Z is equal to 2. And if you look at the graph on the left, when you're measuring degree, you don't account for arrows. So the degree of C would again be 5, just as it is for X. Okay, now in the case of directed graphs, there's a specialization of degree called in degree and out degree. So in degree is the number of edge touches with an incoming arrow, and out degree is the number of edge touches without an incoming arrow. So for instance, at vertex C, the in degree of C is 2, because we count 2 incoming arrows, whereas the out degree of C is all the remaining touches that don't involve incoming arrows, and that would be 3. So one thing you can probably see from this is that if you take the in degree of a vertex and add it to the out degree of a vertex, you get the total degree. Okay, now we're also going to be interested in paths and circuits. So a path essentially is a collection of vertices and joining edges. Like for instance, suppose we want to move from V to X, right? We could go along this edge to Z, and then along this edge to X. So that collection of vertices and joining edges is what's called a path. So a path becomes a circuit if you start and end at the same place. Now an Euler path, remember the Königsberg problem, an Euler path is a path that uses every edge exactly once, whereas an Euler circuit is a circuit that uses every edge exactly once. Now we say that a graph is connected if you can form a path from any vertex to any other vertex. Like for instance, if you select vertices W and Z, should be able, if this graph is connected, I should be able to find a path from W to Z. And in fact, I can. There are a number of paths. In fact, I could go from W down to V and then V over to Z. So a disconnected graph would be maybe something like this. So if I think about the graph consisting of these 3 vertices, let me call them, I don't know, F, G, and H, right? There's no path joining F to H or joining F to G. So this graph here is not a connected graph. We can use our new graph terminology to recount some of Euler's observations about graphs. So there are 4 observations listed here that he made. First is that if you take any graph and you look at the sum of the degrees of the vertices, that's going to be equal to twice the number of edges. That's because each edge contributes 2 to the sum of the degrees. Now, the second observation is if a graph has more than 2 vertices of odd degree, then it cannot have an Euler path. Now, remember, an Euler circuit is a special type of Euler path. So this says that if a graph has more than 2 vertices of odd degree, it does not have an Euler circuit either. The third observation is that if a connected graph has exactly 2 vertices v and w of odd degree, then there is an Euler path from v to w. And then finally, if all of the vertices of a connected graph have even degree, then the graph has an Euler circuit. So what does this say about the Königsberg bridge problem? So remember, that problem was, we were able to transfer that to a problem about a graph. So remember, that graph had vertices B, C, D, and A. And there were 2 edges between A and B, corresponding to 2 bridges between those regions of the city. The same thing with B to C. There are 2 edges. And then there's a single edge from C to D, single edge from A to D, and a single edge from B to D. Okay, so let's look at this graph and consider observations 2, 3, and 4. So first of all, let's figure out what the degrees are of these vertices. So the degree of C looks like the degree of C is equal to 3. The degree of B, we count 1, 2, 3, 4, 5 edge touches, so that's 5. Degree of A would be 3. And the degree of D equals 3. So all of the vertices of this graph are of odd degree. So we look at observation here number 2. Observation number 2 says that if a graph has more than 2 vertices of odd degree, then it does not have any Euler path. So what that means is that the solution to the Königsberg bridge problem is that there is no way to walk the city and cross each bridge exactly one time. Okay. Graphs can be used to do far more than just solve the Königsberg bridge problem. Here on this slide, we see a problem involving scheduling that we'll use graphs to solve. So here you see a list of pairs of classes, and each pair, the 2 classes can't be scheduled at the same time because they often have students in common. So the question that we'd like to solve is, what's the fewest number of time slots needed to schedule these classes? To solve the scheduling problem, we first form a graph of the situation. So the vertices of our graph are going to be the classes in question, and an edge will exist between 2 vertices exactly when the 2 classes in question have many students in common. So to determine the number of, or the fewest number of time slots, what we're going to do is color this graph. So that means that we're going to assign colors to each of the vertices in such a way that no 2 vertices that are joined by an edge have the same color. So we start just doing this. So in the center, why don't we color calculus blue? And now let's suppose I want to color chemistry. Well, I can't color chemistry blue because there's an edge joining calculus to chemistry. So I have to pick another color, let's say green. So I'll color chemistry green. And then we move over, say, to physics. And physics is connected to both calc and chemistry. So I can't color it either blue or green. So let's pick another color, say red. We color that red. Now say we move down to CS. Well, it's connected to both calc and physics by an edge, so I can't color it red or blue, but I could color it green because there's no single edge joining CS, say, to chemistry, right? So I can color that green. Moving downwards to DM, which I guess is discrete math, I know that I can't color it green or blue, but I could color it red. And now we only have 2 more vertices to color. So we look at bio. It's connected to calc and discrete math and to psych. Now I haven't colored psych yet, but I have colored calc and discrete math. And they're both colored blue and red. So I'm going to go ahead and try and color this green. And now let's see if there's a color that we can use for psych. So I know that I can't color it green, but I could color it anything else that I want. So I have my choice here. I could color it red or I could color it blue. Or I could give it some new color altogether. But remember, we're wanting to be as efficient as possible with our colors. So I'm going to go ahead and just color this vertex blue. And so that is a coloring of our graph. So here is our graph coloring again. And now what does it tell us about the time slots? Well, it should say to us now that there are 3 time slots as a minimum that we could use to schedule these classes without significant overlap. So we have a green time slot, a blue time slot, and a red time slot. So in the last example, we solved a scheduling problem, essentially by weighting vertices of a graph with colors. Now, when we take a graph and instead of weighting vertices, we weight the edges somehow, what we wind up with is something called a network. So mileage charts are a pretty good setting for networks. So here on this slide, what you see are is a mileage chart of California cities, Barstow, Eureka, Fresno, Los Angeles, Needles, and San Diego. So the column headers, the B stands for Barstow, E for Eureka, F for Fresno, and so on and so forth. So here this mileage chart is partially filled in. And we can represent this situation using a graph. So we let the vertices represent the towns, of course, and then the edges are weighted by the mileages that were given in the chart between the towns. So like this top edge here between E and F has a 450. That is representative of the fact that on the previous slide we saw it's 450 miles from Eureka to Fresno. So the question is, how far is it from San Diego to Fresno? So that translates to a graph problem where, here's San Diego and here's Fresno. And what we want to do is consider all the paths from San Diego to Fresno, and we want to find the one that minimizes the sum of the weights on the edges. So if you do that, you would probably find that this path from San Diego up through Barstow and then to Fresno minimizes the sum of the distances. We can also use graphs to organize data. In particular, binary search trees are good for organization. So for instance, a spell checker would need to organize data efficiently so that it's easy to find data and it's easy to add new data. So in this example, we're going to use a binary search tree to organize this list of words that you see here alphabetically. So what I recommend that you do now before we go on to the next slide is to write down, make note of this particular list of words in this order. So on this slide, we illustrate how we form a binary tree to organize these words into alphabetical order. So the first thing we do is we start with the first word in our list, which you might remember was macchiato. And that is going to form sort of the top of our binary tree. So we have a vertex associated to that word. So we're done now with that word, and we move to the next word in the list, which was poset. And so you ask yourself, does poset alphabetically come after macchiato or before macchiato? If it comes after macchiato, we move down and to the right. If it comes before, we would move down and to the left. Since it comes after macchiato alphabetically, we move down and to the right and form this vertex with poset and draw an edge joining them. All right, so then we move on to the third letter, or the third word in the list, which was fat. So now we start at the top, we think about macchiato. Does fat come after or before macchiato? If it comes after, which it does, you move down along the existing edge to poset. And then you ask yourself, does fat come after or before poset alphabetically? If it were to come after, then we would move down and to the right. But it comes before, so we move down and to the left, draw the vertex here, and establish this edge in our tree. All right, so now we go to the next word in the list, which was complexify. So we start once again at the top with macchiato. We ask ourselves, does complexify come after macchiato or before macchiato alphabetically? It comes before macchiato, and so we move down and to the left and establish this new vertex at complexify and establish this new edge. All right, so now let's go to the next thing on the list. Next word on the list is jazzed. So I start at macchiato. Jazzed comes before macchiato in the alphabet. So what I do is I move down along this edge to complexify, and I ask myself, does the word jazzed come before or after complexify in the alphabet? And it comes after, so that means that I'm going to move down and to the right, create a new vertex and a new edge, and my word jazzed will be right there. All right, well, let's keep going. We've come this far. So the next word on the list would be sheafify. So I start at the top. Sheafify comes after macchiato, so I move down along this edge to my next comparison word, which is poset. And I ask myself, does sheafify come before or after that word? It comes afterward, and so that means that I need to, since there's no existing edge, or no existing vertex, I establish a new vertex down and to the right. So there's our sheafify word, and I establish this edge going down to it. And then the next and final word in our list is the word clueless. So again, we first compare to macchiato. It comes before macchiato, so we move to the left, down to the next comparison vertex, which would be complexify. Does clueless come before or after complexify? Well, it comes before complexify, so we move down and to the left, which forces us to form that new vertex and the new adjoining edge. So now we're at the end of the list. And if you simply move, now the words are in alphabetical order. If you drop them down vertically, right, take complexify, put it down here next to clueless, put macchiato all the way down here between jazzed and fat, put poset down here. So now you imagine all of those words lined up in a row. They are going to be in alphabetical order. So here we're asked how many comparisons need to be made to search through a balanced binary tree with 255 nodes. So in essence, what we're asked is, well, we have all these vertices here in our binary search tree, and we want to know what it takes to find any given one. So it takes sort of one comparison to find the top node, and then another comparison to find one of the two nodes on the next level. So we have one comparison needed to be made to find that. Another comparison needed to be made in order to find one of these two here. And then at the next level, we need another comparison to get down here. And so if you keep going downward along this fashion, what you'll find is that you need 8 comparisons.